Aloha, my name is Alex Yu. I am a professor of data science and artificial intelligence in Hawaii. In this video I will discuss the role of Google's Tensor Processing Units in artificial intelligence and cloud computing. Artificial intelligence and machine learning rely on a single mathematical backbone, the tensor. A tensor is essentially a multidimensional array, a generalized form of scalars, 0D, vectors, 1D, and matrices, 2D. In deep learning, tensors represent everything from input data, images, sound waves, text tokens, to the learned parameters that define a neural network's knowledge. The computations that update these tensors, multiplying and summing enormous arrays of numbers, are extraordinarily intensive. Standard CPUs, optimized for sequential tasks, quickly hit their limits. Even powerful GPUs, designed for parallel graphics rendering, can struggle with the scale and precision required for modern large language models, LLMs. This computational bottleneck led Google to design its own specialized hardware, the Tensor Processing Unit, TPU. Introduced in 2015 and refined through multiple generations, such as the current TPU v4, and the newer TPU version 5e and TPU version 5p. The TPU is a domain-specific accelerator built to execute tensor operations at massive scale and with remarkable energy efficiency. The heart of each TPU is the matrix multiply unit, MXU, which can perform tens or even hundreds of trillions of multiply accumulate operations per second, ideal for the dense linear algebra behind neural networks. TPUs are tightly integrated with high-bandwidth memory and interconnects that allow thousands of chips to communicate efficiently in TPU pods, forming supercomputers purpose-built for AI. A critical component of the TPU ecosystem is the XLA, Accelerated Linear Algebra, compiler. This compiler works seamlessly with frameworks like TensorFlow and JAX to automatically optimize the neural network's computational graph, turning high-level operations into the highly efficient low-level matrix multiplications that the TPU's MXU is designed to execute. This tight integration of custom hardware and optimized software is a key source of the TPU's performance advantage. Furthermore, while initially focused on model training, modern TPU generations like the TPU version 5e are also increasingly optimized for high-volume inference, the process of running a trained model to generate immediate results. Within Google Cloud, these pods serve as the computational core for large-scale AI services like Google Search, Translate, Photos, and Gemini. By offering TPUs as part of its cloud portfolio, Google effectively exports its internal machine learning infrastructure to researchers, developers, and companies worldwide. Although TPUs were originally engineered for Google's in-house applications, they now power external projects as well, most notably Anthropic's Claude models. In 2025, Anthropic expanded its partnership with Google Cloud, signing a multi-year deal to access up to 1 million TPUs. This decision might seem paradoxical. Anthropic's Claude directly competes with Google's Gemini, so why would Google arm a rival with its best hardware? The answer lies in understanding Google's dual identity. On one side, Google DeepMind develops AI products that compete in the consumer and enterprise chatbot markets. On the other, Google Cloud operates as a neutral, revenue-driven infrastructure provider, akin to a public utility. In that sense, Google selling TPU compute time to Anthropic is less like the United States selling missiles to Russia and more like Boeing selling aircraft to both United Airlines and Delta Airlines. The two may compete for passengers, but both buy from the same manufacturer. Notably, Anthropic employs a multi-cloud and multi-chip strategy, utilizing Amazon's Trainium chips and NVIDIA GPUs alongside Google's TPUs. This diversified approach confirms Google Cloud benefits financially and strategically by hosting Anthropic's workload. It validates TPU performance, strengthens Google Cloud's reputation, and keeps Anthropic within the broader US AI ecosystem, where rivalry coexists with shared technological foundations. For the general public and students, TPUs are not a remote or inaccessible technology. Google Colab, a free online coding environment, provides users with the option to run computations on TPUs. With just a few lines of setup code, students can train neural networks on the same architecture that powers Google's billion-parameter models. This democratization of high-performance computing has transformed AI education. Graduate students can now experiment with convolutional networks, transformers, and diffusion models on world-class hardware, without owning a single GPU. It also encourages reproducible research, since results obtained on Colab's TPUs can be scaled up seamlessly in Google Cloud for industrial or academic projects. Looking ahead, TPUs are poised to remain a critical pillar in the AI infrastructure landscape. The upcoming TPU architecture, including the 7th-generation TPU, Ironwood, reportedly promises major leaps in speed, scalability, and power efficiency, rivaling NVIDIA's most advanced GPUs while remaining tightly integrated with frameworks like TensorFlow and JAX and the XLA compiler. The broader pattern emerging is one of co-opetition, cooperative competition, where major AI players share infrastructure while contesting markets and ideas. For graduate students and researchers, understanding TPUs is thus more than a hardware topic. It is a window into the evolving economics and geopolitics of AI. What are your thoughts? Does this model of shared infrastructure accelerate innovation, or will the balance between openness and rivalry eventually fracture? Please leave your comments here. If you found this video informative, please like, share, and subscribe.